Hello, welcome back. In the last segment, we looked at selection using the if-else statement, including the relational operators that we're going to use to make decisions to control the flow of control. It might not have been obvious to you exactly when you would get to use one of these, so we're going to take an entire segment now to solve a couple of problems using if-else statements and relational operators. So here's our first problem statement. It's just for fun and it's very small. We're not even going to make an input process output diagram for this. So we're going to write a program that will do the following. Ask the user how old they are. And then the user will type their age. And if they are 21 or older, print a message that they can buy some beer. If they're not old enough, print a message telling them that they have to be 21 to buy beer. So we're going to write an if statement that compares their age to the number 21 using relational operators. Okay, let's go into the development environment. We'll take this spec with us as a comment in the program, and we'll solve this simple problem and get a program running that uses an if statement. Okay, here we are in the development environment, and I've started a new project called Beer, and I copied the spec in here as a comment. So this is a block comment. You can tell if it turns green that the compiler is going to ignore it. So you might want to pause this now and go and make the first part of this program so that we can work along together at solving this specification. Okay, the first thing that we have to do is to ask the user how old they are, and presumably we're going to store that value in a variable. You need to declare your variables before we use them, so let's make a variable called age, and then we will make the prompt, and we learned in the segment on input and output that you commonly will prompt the user for what they're expected to enter. So enter your age, just like that. Nothing too complicated. The lowercase n would be better. In fact, required. And now we're going to scan the value that they type, scanf, into that variable. So let's put %i, and remember that we need an ampersand before the name of the variable when we're doing an input statement. Okay, so we have the person's age, if we got all of that right, in the variable age. And now, let's look at the spec again. It says, if they are 21 or older, print a message that they can buy some beer. So we want to make an if statement here. We're going to say if, and I like to make a fill-in-the-blank problem, so we can write if something is true, then do something else. So now, what do we need to express here? A relational expression, and in the spec, if they are 21 or older. So how will we write that? We have the variable age, and we're going to compare it somehow to the number 21. So if age is greater than 21, is that what we want? How about greater than or equal to? Does that feel better? Age is greater than or equal to 21. That means that they are old enough to buy beer. And I guess I'm working in the state of Florida, so maybe you have different rules wherever you are. Printf, what are we supposed to do? Print a message that they can buy some beer. Okay, you can buy some beer. Exclamation point, and let's put a carriage return, a \n. And why don't we test that and see if it's doing what we expect it to do. So we're going to compile with F7, and I'll make this a little bit bigger so that we can see that I did not make any syntax errors in my typing. And then if we hit F5, we can run this, and it says enter your age. Let's put 34 and enter, and it outputs you can buy some beer. Let's run it again with F5. Enter your age. If I'm 14, it doesn't print out the message that you can buy some beer, so our if statement probably is working. We'll check it in the debugger. And I'm going to put a break statement there, or a breakpoint, sorry, right on this if statement. And we'll run up to that statement. So let's put F5 again, and it will say enter your age. Even though we're using the debugger, we still have to play the part of the person who is executing the program. So enter your age 21, and when I hit carriage return that time, what happened? There, we hit the breakpoint. The variable age does have the value 21 in it. You can hover over it and see that it has the right value, or you can look down here. So 21 is greater than or equal to 21. Is that true or false? Well, it's true because they are equal. And now if we step over, we'll see that we're going to execute the printf statement, you can buy some beer. This debugging can really save you a lot of time. So you can see immediately that the program is doing what you expect. Now, let's look at the rest of the spec. If they're not old enough, print out a message telling them they have to be 21 or older. So there are a couple of ways of doing this. Let's do it the not so good way first. So we could write if age is less than 21 and braces, which we don't really need because we're controlling only one line of code. Printf, you are not old enough. Put a carriage return. Now, let's see, would this work? So if we're 21 or older, it would output you can buy some beer. And then we test for less than 21 and say you're not old enough. Okay, let's run that, and I'll run it without the debugger this time. We'll turn off that breakpoint, and oh, there are build errors. What did I do wrong? This is a good exercise. Find the bug. Okay, the colors help. Let's compile this. F7. None failed that time. And now let's run it with F5. Good. Enter your age. So this time, if we're 14, it prints out you're not old enough. Let's run it again. F5. 21. You can buy some beer. Let's run it again, just for fun. If we're 123, you're old enough to buy beer if you're 123. Okay, so we have two if statements, one for if you're greater than or equal to 21 years old, and the other one if you're less than 21 years old. What I'm hoping you're saying is we didn't need this if statement. We could have used a true part and a false part for this condition. So this age is less than 21 is always going to be true when this one is false. So let's take that if statement out, and instead we'll make it an else that is associated with this if. So if age is greater than or equal to 21, do this, else do this. And because we have only one statement here on each of the if and else, we didn't need any of these braces. So those are there now only for readability. Let's run this now with the if and the else, and we'll run in the debugger. So F7, let's make sure that I didn't do any typing errors. And F5, enter your age. If we are 20, now we've hit the breakpoint. Age is 20, greater than or equal to 21. 20 is greater than or equal to 21. True or false? Well, it's false, so if we go to the next line of code, step over, it will jump us down to the false part, or the else part, that's associated with that if. We're going to look at another problem specification now. This one will be just a little more interesting than the last one, and we'll get to use some of the tools that we had looked at in a previous segment for breaking down a problem that's a little bit more complex. So in this one, we're going to calculate income tax. So have a look at the specification. Ask the user how much money they made last year. Calculate their income tax. If they earned less than $15,000, the tax is 0. So far, that's easy. If they earn $15,000 or more, but less than $25,000, their tax rate will be 15%. And if they earn $25,000 or more, their tax rate will be 20%. Output the amount of tax that the user will have to pay and their net income. The net income is the income minus the tax. Okay, this problem is complicated enough that we'll use an IPO, or an input process output diagram. So I copied the spec over to this slide, and I usually start out by looking at the spec and finding out what are the inputs and outputs. So in the first line in the spec says, ask the user how much money they made last year. So that's an input into the program, and I put under the input column income. It's the only one that there is in this spec. Now, what are the outputs? And near the end it says output the amount of tax that the user will have to pay and their net income. So I put two variable names under output, income tax and net income. And now the interesting part of this one is, how do we get what's in the middle? How do we process this input and produce an output? And it says in the spec, less than 15,000, the tax is 0. So we can write that as a summary in the process. If income is less than 15,000, calculate the tax, and then else. If it's 25,000 or more, calculate the tax, else calculate the tax for the middle range, and then calculate the net income and do the outputs. So the amount of time that you spend getting this processing diagram correct, or the IPO diagram correct, will save you time in writing the code. And if you don't get it quite correct, then you'll write the code and you'll find out, well, I'm not getting quite the right answers, and you'll have to go back and forth a little bit. That's a natural process. Me presenting an IPO that's already correct, and I checked it before I recorded this, is a little bit kind of a fake way of solving the problem. It's not a one-pass process. You try it, you make a mistake, and you come back. When we break down the problems and try and make it as a single pass process as possible, it's not really ever going to be that. You're going to go through the process and come back and go through it again, correcting the mistakes. So the next step, after we have what looks like a reasonable IPO diagram, is to make some test cases. So I took part of the spec onto this slide, and if we, in a test case, you'll recall, we want to suggest what the user might enter as the inputs, and then say what the expected results would be given that input. So if the user entered 12,000, we would expect this program to calculate 0 income tax, and the net income is still 12,000. In the second test case, a little more interesting, if the user enters 25,000, what would their tax rate be, and what would their tax be? So go back up to the spec. The last line says if they earn $25,000 or more, the tax rate will be 20%. If you multiply that 25,000 by 0.2, you'll get 5,000, which is the tax. And we expect our program to output $5,000 tax and a net income of $20,000. And in case 3, $30,000, $6,000 tax and a net income of $24,000. Several test cases to make sure that we really understand what we're doing. Probably a couple more test cases would be useful for this particular problem. So what we're going to do now is we're going to go into the development environment, and we will take with us the IPO, at least the processing part, and we will develop the code based on the processing part and hope to get the result that's expected according to these test cases. Okay, here we are in the development environment, and I've created a new project called income tax and a file called incometax.c, and we're going to go from this slide that gives us the IPO diagram to the back and forth to the development environment as we solve this problem. So let's start off by declaring the variables income, income tax, and net income. And we're going to use double for these. It's possible that you could have a dollars and cents income, but we'll just use dollars for now. So income, income tax, and net income. Notice that the convention is starting your variables with lowercase letters and using the uppercase for each subsequent word in the variables. You can't put a space in your variable name. It will give you some cryptic errors that are hard to understand. So we've got income, income tax, and net income. So under the process part now, it says ask the user for their income. Let's go and do that first. Let's put the prompt printf, enter your income, and a \n, and now we'll scan in what the user types. So scanf, and do you remember what we'll use for a double variable in a scanf? We'll use %lf, and now an ampersand before the name of the variable income. And let's see, maybe we should output that right away to make sure that we got that right. How about your income is %.2lf \n. And if you're remembering this from the segment on input-output, you can force the format on output. So the %.2lf indicates that we're going to use 2 places past the decimal, but you can't force the input, the format of the input. So we just have %lf here, and we have %.2lf on the output. And the input statement needs an ampersand, the output cannot have an ampersand. And okay, so now we've got the income that we can start processing with. We want to calculate the income tax and the net income based on the rules in the specification. And it says if the income is less than 15,000, calculate the tax. Okay, so if income, something to do with 15,000, and I should have mentioned before, and it only occurs to me now, that you may not put commas in your literals. So 15,000 is not going to work. We have an if statement that's going to compare income with 15,000. And if we say greater than, let's try that one. No, less than, let's try that one. If income is less than 15,000, that's what we have in our spec. If income is less than 15,000, calculate the tax. So we might say that income tax gets 0. Okay. Now what? Else, if it's 25,000 or more, calculate the tax. If it's 25,000 or more, the tax rate will be 20%. Let's write else if income is 25,000 or more, greater than or equal to 25,000, then we'll calculate the tax. Income tax gets, well, what is the income tax? Income times 0.2, which is 20%. You can put another 0 there if you want to. It won't make any difference. So we've got income tax is income times 20%. Back to the spec. I mean the IPO. Calculate the tax for the mid-range. Let's put else income tax is income times 15%. And we have a fairly interesting flow of control here for the 3 different cases. So if it's less than 15,000, then the income tax is 0. If it's more than 15,000, then we're going to go and do the else part. So if the income is greater than 25,000, the income tax is 20%. Else the income tax is 15%. So this is the mid-range, this is the low range, and this is the upper range. The net income is the income minus the income tax. Typo there, minus the income tax. And now the last thing in our process column is to output the income tax and the net income. So printf the income tax, and let's put %.2lf \n. And the other one, the net income, %.2lf Okay, I suspect that I probably made some typing errors in all of this, so let's do an F7 and see if we get, well, 1 succeeded, 0 failed. So my typing is fairly accurate today. I don't expect you to be typing this much code without getting some compiler errors. And when you do, go to the first one. Check on the first compiler error because it probably caused all of the rest. Okay, now what we need to do is see what this program is doing for each of our test cases. So let's go back to the slide and say our first test case is 12,000. We expect the income tax to be 0 and the net income to be 12,000. Let's try that case first, and we're going to try it in the debugger. So let's put a breakpoint here and hit F5. Enter your income, $12,000. Don't put a comma there. We just want the number without any formatting on it. So income is $12,000 with a bunch of zeros after the decimal point. And let's see if the calculations are going to be correct. So we've stopped at this breakpoint. Income, 12,000, is less than 15,000. Is that true or false? Well, it's true. So if we do step over, income tax gets 0. That seems to make sense. And the false part of the if, we won't do that at all because we did the true part. The net income is the income, 12,000, minus the income tax, which is 0. Execute that statement, the one being pointed at, and now we can output the income tax and the net income. I didn't put a pause at the bottom of this program, but since we're in the debugger, it's paused anyway. So I can flip over to the execution of the program and see if it's worked for us. So the income of 12,000, the income tax is 0, and the net income is 12,000. So in the simplest case, the program seems to be working. Now let's look at another test case. 25,000, our income tax should be 5,000. Let's see if that's going to work for us. So we're going to run the program, enter the income of 25,000 without any commas, and we'll go back and see, follow the logic. Income is 25,000. Is that less than 15,000? No. So when we execute that if statement, we should go to the false part, which is the else part. So now 25,000 is greater than or equal to 25,000. Is that true or false? That's true because it is equal. So when we execute this if statement, we should go to the next line. Income tax is income times 20% or 0.2. Let's execute that line of code. And the variable income tax now has the value 5,000 in it. See, it's very convenient as you walk through this line by line to make sure that you have the correct calculations or what you expected the calculations to be as you're executing it. What will we do after this else? Will we execute this line of code? No, because we did the true part, we won't do the false part. So when we execute the else, we'll skip over that, calculate the net income, and then do the outputs. And let's flip around now and see the income tax is 5,000 and the net income is 20,000. Verify on the test case that that's what you were hoping for. And indeed, we hoped for the net income of 20,000. Well, as I typed this, I don't want you to think that a problem of this complexity should be something that you would sit down and just type in without making any syntax errors and having the logic correct. That's not going to happen. What will happen is you will type something and you'll get the syntax errors taken out of it, and then you'll have the logic and it won't be correct. And you really have to work on how to make these if-else statements do what you need them to do to meet the specifications. So it's not going to happen as easily as it happened with me typing and you hopefully typing at the same time and flipping back and forth. It is going to take several attempts for you to develop the skill of writing these if-else statements to express the logic that you need. Let's talk for a minute now about software quality assurance, or QA. QA is the process that assures that the software is doing what it's supposed to be doing. And this is typically done by a non-programmer. The test cases that guarantee that the software is correct are made by an expert in the domain of that software. So consider the problem that we just solved. A very simple income tax calculation problem, but we're all aware of the complexities of income tax as a software problem. So the person who decides what should the output be from a program that's calculating the income tax is going to be a tax attorney. It's not going to be a programmer. So the tax attorney will be making the test cases that say, if I put these inputs into that program, I really need these outputs because that's what the current tax legislation says should be calculated. So this is quite a different process. This is an additional process from the programming part. It's the software quality assurance part, and the people doing QA in software are probably not the programmers. They're the people who are trying to assure that the software is correct. It's the responsibility of the programmer to do as well as they can to meet the specifications that they're given. Sometimes the specifications, in fact, as a rule, the specifications will not be as precise as they need them to be to get the exact result. And then the software QA people, the quality assurance people, come in and they say, okay, this is what you would have to change to make the software correct. And it's part of the software lifecycle. The QA engineers, sometimes they are programmers who have gone into testing or software testing, and sometimes they're domain experts. It depends on what kind of software it is, whether you need a domain expert like a tax attorney to come in and decide whether your software is doing what it should be doing or not, or it might be something that's fairly simple, just a very logical person who understands what software, how software works. Could be your software quality assurance engineer. Okay, let's think about the concepts that we covered in this segment. We were solving problems using selection, so if statements with relational operators, relational expressions, and else statements. And what you should be taking away from this segment is that you should be building enough test cases so that you thoroughly will understand what the problem statement is asking for. And your test cases should test the boundaries of the specification. So in the example we used with income tax, we tested 25,000 to make sure that it was falling on the right side of the possible tax rates. An interactive debugger, walking through the code, watching it execute line by line is just very, very valuable. This is a skill that you should learn right at the beginning. I tell my students, if you want to waste more than half your time, then don't bother to use the debugging tools that you have. And it isn't funny. Wasting more than half your time is not funny. So get comfortable using the debugger in the development environment and watch what the code is doing. And it's just it's an incredibly valuable tool to help you have confidence that the lines of code that you're writing are doing what you expect them to do. And now here at the end of this segment, we've talked about the software quality assurance process. And this is partly Well, the software programmers are required to write software that's as close to the spec as they can, and if the spec is exact, then the software should be exact. And a lot of the times, the specifications are not exact, and the programmer should come as close to what they think it should be doing as possible, based on all reasonable assumptions. And then the software quality assurance process will ensure that the code or the software is doing what it really needs to be doing for a releasable product. This last statement on this slide may be too obvious for you, but you should keep the specification and the input process output diagram next to you while you're writing the code. And I put that there specifically because a lot of students will read the specification, and then as they're developing the solution, they actually forget what the specification was, and they come up with an answer that doesn't match what originally they were being asked for. So as you are working on developing your logic skills and writing if statements with else clauses and so on, you may not be remembering what the problem originally was. So keep that handy and keep going back and forth. I'll see you next time.